All right, welcome everyone. So we're going to look at this example here and how we can use spring potential energy in solving a problem. So here we have an archer pulling back the spring on her bow, a distance of 0.7 meters from its equilibrium position. To hold the string at this position, it takes a force of 140 newtons. How fast will the arrow be moving when it's released from the bow? I'm assuming this occurs at the relaxed position of the string. So something to note here is we are starting things off with an assumption. We're going to assume that this bow behaves like a spring. The string behaves like a spring. Of course, it's the two words that I always mix up. So the string behaves like a spring. So just kind of, first jotting down things we know. All right, we know the mass of the bow being 2.5 times 10 to the negative 2 kilograms. We know how much the bow is stretched from equilibrium. So if it's behaving like a spring, this is the spring's displacement from its relaxed position. So delta x, we'll call it, right? Or if we're looking at this formula the way I've written it above, it's just the value of x. And finally, we're told that the force it takes to hold the spring at this position is 140 newtons. And I'll sublabel that force in actually just a moment here. So sketching things out, I'm not really sure how bow and arrows work too much, but there's my bow. There's the string on the bow, and here it is in its relaxed position. So if we have an arrow here, actually I'm not even going to draw the arrow because I'm going to confuse it with vectors. But the arrow here would be pointing leftward. Now, my understanding is you pull the string backwards. So right now, first the arrow starts here, and then the arrow is kind of pulled back to this location here, where it's pulled back a distance of 0.7 meters. And so then the string here, if we were to release the arrow would then launch leftward because of this force acting on it. So in terms of a free body diagram for the arrow, right, we've got at the moment of time when it's kind of ready to launch, we have the force due to the string acting leftward. We always have the force of gravity acting on an object, straight down, which means we have to have some sort of force upward to compensate the gravitational force only because we know the arrow is going to launch straight to the left. So this force here, we'll call, maybe it's the force of the hand, or the force of the fingers holding it there, whatever you want to mention. So this value in the problem of 140 newtons, that's the force due to the string, because that's the force needed to hold the object back. So when it's released, the value for the spring force and the string force is going to be that. All right, so that is the 140 newtons. So I'm going to use, again, work energy theorem here to solve this problem. So first I want to define my system. So my system, well, for sure we need the arrow to be in our system because that's the object we're analyzing the motion of. And so looking at our free body diagram, right now including the arrow in our system means all those forces would be external. We don't have the means of having the spring force be external, right? Because this force due to a spring depends on position. So it's constantly changing. So I want to include, the arrow and let's say the bow. So that string then is in our system. So therefore that spring force will be internal to our system. That'll be helpful for us. The other two forces here will not include the hand in our system and will not include the earth in our system. So our system is entirely just the bow and arrow. So if we list internal and external forces, all right, so we have three forces we're concerned with here. we have the force of the hand. So that's the interaction between the arrow and the hand. Hand is not in our system, so that is an external force. We have the gravitational force. So that's an interaction between the arrow and the earth. Earth is not in our system. This is an external force. Whoops, that should be gravity. And then finally, we have the force due to the string. This force is internal because the bow, along with its string, is in our system. So this is an internal force. All right. So this is useful to us because when we're applying the work-energy theorem, these two lists will help us distinguish what goes on the left-hand side here for work and what goes on the right-hand here for change in energy. Work is done by external forces. So work, we need to consider the work done by the force of the hand and the work done by the gravitational force. On the right-hand side here, we have to think about change in energy. We always consider change in kinetic energy, but then we also have we have to consider potential energy as well. And potential energy, remember, is associated with internal forces. So the force due to the string, which is behaving like a spring. So we need to deal with the change in spring potential energy here. So this list helped us figure out what's on the left and what's on the right. Now what's really convenient about the left-hand side here is that the force of the hand, so our arrow displaces leftward. So the force of the hand and the gravitational force are perpendicular to that. Whenever the force and the displacement are perpendicular to each other, the value for the work of those forces is 0. So my entirety of the left-hand side here is 0. So that's very convenient. And this is equal to change in kinetic energy. All right. Well, the bow initially starts from rest because it's being released from when it's pulled back. So when we deal with final energy minus initial kinetic energy, the initial kinetic energy will be 0. And our change in spring potential energy. So we add to that our final spring potential energy, subtract from it our initial spring potential energy. Well, at its initial location, we do have potential energy because it is pulled back. That's our initial location. Where the final location now, it's when it's at its relaxed location. So there's no potential energy associated with that because x in the formula is 0. That's this displacement from its equilibrium, from its relaxed position. So our formula here simplifies to being just the final kinetic energy minus the final, that should be initial. Geez, I gotta keep my subscripts straight. So it's the final kinetic energy minus the initial spring potential energy. So that is 1/2 mvf squared, where I'm trying to find that vf, minus mg x initial, or just x. It's that 0.7 meters. All right. So, I'm not writing the right thing, am I? Hopefully you caught my mistake. I wrote down gravitational potential energy. We're not dealing with that. We don't have any change in height. In fact, our gravitational force doesn't add or remove any energy from our system. This should be 1/2 kx squared. Okay. But looking at this, we know everything except for 2 things. We don't know the speed, which is what we're solving for, and we don't know, and we don't know the spring constant. So we actually need to solve for the spring constant first. Luckily, that's pretty straightforward. I'm going to write on the top here, because the force due to the spring, which I'm just calling Fs, is just equal to k times x. So k is just going to be the spring force divided by x. So plugging that in, I've got, actually putting this on the left-hand side, 1/2 times K, which we said is the spring force divided by X, multiplied by X squared, is equal to 1/2 mVF squared. So I've got some things simplifying here. So first, the 1/2s cancel out, but then I have one of the x's canceling out. So we have spring force times displacement is equal to mv squared. So that simply leads us then to the relationship here that the speed is equal to the square root of the spring force divided by x, multiplied by x divided by m. So this is 140 newtons. I'm going to be sloppy here, times 0.7 meters divided by the 2.5 times 10 to the negative 2. That ends up giving us 62.6 meters per second as the speed the arrow has as it leaves the bow. All right, so I hope that was helpful in seeing how we can use spring potential energy in problem solving.